перспективы нас ожидают с внедрением новых технологий в привычные
What
сферы?
kind of forecasts do we await with new technologies in our life? How security and cybersecurity will change? We will continue with quantum technologies. Let us welcome speakers Ekaterina Snegireva, Senior Analyst at Positive Technologies, Anton Guglya, CEO at QApp.
Здравствуйте, коллеги. Очень приятно видеть вас сегодня в субботу.
Good afternoon, dear colleagues. It's a great pleasure for me to see you here listening to quantum technology presentation. Quantum technologies are very well developed all over the world, and by raise of hand, do you know that we have first quantum computers here in Russia? Great, that's the majority of the audience. Quantum technologies are not just about quantum computer, it's all about quantum distribution of keys, quantum security, post-quantum encryption algorithms that are just basically and partially quantum. It's all about sensors, and all that is being developed both in the technical area. Regulations are also being developed, and the more mature these technologies become, the more relevant question is about their information security. Together with Positive Technologies, we are a group of vendors, first quantum startups that develop different aspects of quantum technologies. We work in universities, physical and technical universities, and altogether we created a report on security of quantum technologies compared to the classical information security and to quantum technologies. We looked into the future and how do we protect from the threats of today and tomorrow. We will speak about this during this presentation, and after that you'll be able to look through the presentation. It's already published on Positive Hack Days, and you can even find the printed version too. And now let us begin. A few words about ourselves. My name is Ekaterina Snegireva. I'm Senior Analyst of a research group at the Department of Analytics at Positive Technologies, and I mainly work with analyst research and reports, and I'm also author and co-author of more than 10 analytical reports for our official website. And today we would like to tell you about security of quantum technologies together with Anton. And Anton, please, a few words about yourself. Yes, my name is Anton Guglya. I manage business in multiple companies. One of them works with post-quantum encryption. This is asymmetric encryption. And another company works with quantum calculations. These are regarding digital twins. And we'll also speak about digital twins later. Altogether, we want to tell you about the future of quantum technologies, what's already here, and to put emphasis on the protection from the threats of today and tomorrow. What do we mean when we say quantum technologies, and what you can find in the report? First of all, we will speak about quantum calculations. Quantum calculations are a group of technologies that's connected with quantum computers. They have new processing power and capabilities that allow it to solve problems better compared to the classical computers. But not all of them. Partially, quantum computers will be able to solve it better. Quantum calculations also have sub-technologies that's connected to the emulation of programs. Quantum calculations also have technologies connected to the interface, access interface to quantum computers or the program emulators that's called cloud services or cloud platforms for platforms for quantum computing, and we'll be talking about quantum computer later. We'll also cover quantum communication. First of all, it's quantum distribution of keys, an ability to use these open channels and different technology that's already available and can be connected with the quantum key distribution, for example, random key distribution, the tools that can provide true entropy. We'll be covering quantum technologies, and post-quantum technologies are not really about quantum, it's more about new technologies rather than quantum physics. But when we're talking about quantum robustness, the industry and academia are considering this in synergy for quantum algorithms and post-quantum algorithms. We will not cover quantum sensors, not because they are not worthy of our attention or not because we don't believe that it will develop. First of all, we wanted to take a look at the technologies that are developed here in Russia, that have already pilot projects, test projects in different universities and research institutes for data protection and information protection too. A few words regarding the quantum technologies themselves. What is that? I think those who know that we already have first quantum computer, we mean that we have technologies that are based on the control of a single most particles of our world, like ions, photons, and we can build new technologies on these particles, like superposition, quantum entanglement, allow us to create these technologies. And obviously, we dedicated our report and our research to these technologies. Quantum computers potentially can solve problems faster compared to the classical computers. And currently, the computers which we have in Russia are not powerful enough. This is just test examples, test samples. They have calculations. There is a number and range of examples that were performed, but currently they are not used. But speaking about the global experience, there are global computers that are better and faster compared to the Russian computers. It doesn't mean that we won't have those, but this is the current state of the situation. Quantum computers are built using different architecture, cold atoms, superconductors, and many different architectures, and academia still decides which architecture will be the priority, what kind of architecture will have the most powerful capabilities. And this technology, you just have to accept it, that in parallel, in the world and in Russia, almost all the priorities, almost all potential architectures are being developed right now. It is important to note that in Russia, there are no scaled solutions. We only have single examples, like ion computer that uses ion traps. We have a single example, and it takes, well, basically the whole stage, like here in Luzhniki. It's not a miniature version of it. And we don't really have companies that would have this conveyor solution, and they do not solve strategic goals with small quantum computers. We already solve quantum transformers. We saw also educational samples, but they have only 1 or 2 qubits, and this is not enough. So the laws which are used for these calculations, like superposition or quantum entanglement, are used for quantum communications too. Now we understand the level of quantum technologies, and let's speak about security. First and foremost, let's start with cybersecurity for quantum computers, their emulators and interface in order to access them. How do quantum computers perform calculations? Currently, quantum computers are a hybrid of classical systems and quantum systems. It means that classical computer passes parts of some problems for quantum calculations. In general, the calculations are as follows. First, we need to create an algorithm using quantum programming languages. Those kind of languages, and they already exist, like QApp, are adapted to specialized principles of quantum mechanics, like quantum entanglement and superposition. Next, after we've created an algorithm, we have the compilation of that algorithm in a quantum scheme. Quantum scheme or quantum chain is a sequence of logical operations with the usage of qubits. For example, it's initialization of qubits with known values. After that, quantum chain is passed for running for quantum processor. At this stage, quantum entanglement and initialized qubits interact with each other in a complex way, and after that, we measure the results. Basically, we see the current state of qubits, and then we pass these results of the calculations, and then we pass the results to the classical computer as a classical sequence of bits. So what could be the cyber threats at the classical and quantum levels? The point of the matter is that, just as Anton mentioned, researchers work with different types of qubits, superconductors, ion-trapped photons, but no one has demonstrated the best-case scenario. What should we do in order to get a robust quantum computer? That is why the physical level threats are connected with very childlike problems of technologies like instability of qubits, errors of valves and qubit measurements, or potential malicious users could have different cyber attacks if they use sensitivity of quantum computers to heat. At the level of chains, the main problem is loss of credentials or theft of credentials. The point is that in quantum links and quantum chains, they are designed in order to solve specific problems. And if you compromise quantum chain, then potential criminal could find information about the problem at hand. And this is the problem with untrustworthy compilers. So next point is more interesting. When we're talking about cyber threats at the program level, then the spectrum is much wider. As I mentioned, current state-of-the-art quantum computers are hybrid systems that consist of classical and quantum objects. As a result, many cyber threats we are already aware of can also affect quantum interface too. For example, exploiting vulnerabilities of software. As a result of exploiting this software, a malicious user can steal information or results of the calculations, or maybe information regarding the problem itself, get access to sensitive calculation resources, or maybe just stop the hardware or inject some kind of malware. And I must say that in some solutions, in some cases, we're able to find potential vulnerabilities. Another important problem to tackle are attacks at cloud services. Cloud computers that currently work and operate technically are very complex and sophisticated systems, and they can only work in special laboratory conditions. And that is the reason why it is impossible to just place this big computer just like a main stage here in Luzhniki. And that's why companies will use cloud calculations, and obviously malicious users will try to hack them, and thus decrease number of attacks at cloud calculations and platforms. Next up, let us talk about quantum communications. Anton, please, what's quantum distribution of keys and why do we need this? Yes. First of all, when we are talking about quantum communication, we mean that this is some kind of technology to distribute cryptographic channel using open channels like Earth to space, and we already have the results. They can also use normal internet channels. We have these results in Russia, we have results in other countries. In any case, quantum technologies allow to distribute cryptographic key faster in a more secure way. For example, on specific states using photons, these keys are used sort or are sort channels, then the keys get in traditional infrastructure, traditional encryptors, and then it goes up in the infrastructure. Quantum distribution of keys is a technology that's controlled by regulators in Russia. We already have draft standards, new standards that will define the way for quantum communications. And still they do it at the top level. They work with the traditional stack of development and languages. So that's why they have potential vulnerabilities for classical computers and problems that require our attention from the quantum side. Okay, now let's get back to cybersecurity. Speaking about attacks on quantum distribution of keys, then potential criminals use imperfection in optical or hardware elements of the infrastructure and also vulnerabilities in protocols when transferring information. And attacking quantum key distribution can be separated into main areas. First, you can attack the quantum channel of the communication, and you can attack the hardware of the sender and recipient of the communication element. And the first case example are more interesting. You can separate number of ions, or you can blind avalanche detectors. Here, researchers are actively engaged in improving quantum communication channels. For example, in 2022, Russian scientists from a Russian center, together with Chinese and Taiwanese colleagues, worked on this, one of these ways to prevent attacks. In the future, we will have quantum internet, which basically means that it will be a joint quantum network, different vendors in a single network. The targets of potential criminals would be similar to the classical internet: to steal information, to stop different nodes from working, or maybe capture resources and networks. Here we could have the same types of attacks, just like we see currently in the classical internet, but the implementation will be different if we take into account the quantum nature. For example, quantum denial of service would be aimed to stop the hardware, but potential criminals could transfer resourceful task and thus basically overheat it. Or malicious application attack means that a potential criminal could infect the quantum computer with malware. Next point is about post-quantum cryptography. This is a part of research which is not directly using quantum effects, but it's appeared due to the development in quantum technologies, and Anton will cover it in details. Despite the development of quantum calculations, and we believe that first and foremost, in order to solve business tasks, governmental tasks, there is a new risk for cybersecurity, and it's called quantum threats. This is not what we came up with. This is a global terminology, especially in the quantum community. This is an ability for criminals, potential criminals, to use quantum computers in order to have attacks versus encryption elements like digital signature. There is a single attack that's called you save data now and you break it later. When we're talking about quantum attacks, usually you hack later. What it means? Currently, they can go through the current traffic, but once they have access to quantum computer, they can decrypt this data. And this access can be gained through multiple ways. They can be a member of a laboratory that has a quantum computer. They can use social engineering, maybe bribe someone who has direct access to a quantum computer. And they can also have remote access to quantum computing, because currently there is a trend to develop this remote access to quantum computers. As we said, quantum computers have to be screened from lots of external effects. They have to be maintained within within certain temperature. There has to be closed loop and closed perimeter for this quantum system. And that is why we are working on cloud platforms. There are big vendors, global companies, and you probably know about them. They provide access to classical calculations, but they also provide an experimental access to quantum calculations. We also have this first examples where you could access to the cloud platform and get quantum qualifications and quantum calculations. And potential criminals could use this. Mathematical approaches which were used and known before, and some of them were known tens of years before, and some of them are very new. They could help develop new methods of asymmetric cryptography. These developments are going on both in Russia and in other countries, and if we take a look at the state standards, they already have new ideas and they are passing new laws. The National Center of Cryptography works on post-quantum cryptography, and soon we might have a contest on selecting the most robust quantum cryptography methods. And actually, the post-quantum cryptography doesn't really have anything in quantum. It's traditional stack of programming, but at the level of mathematics, at the level of algorithms, they use new technologies. Those technologies, even though the quantum communication are specific hardware solutions that use quantum physics, but post-quantum algorithms that use traditional classical approach, they are not in contradiction with each other. You can use both of them. You can use them separately, depending on the level of the work. For example, if we are talking about endpoint applications, we are talking about client-to-server communication, it's easier and cheaper to use post-quantum algorithms. But when we are talking about strategic approaches, when we are talking about quantum key distribution, it's better to use quantum technologies. There is also synergy between quantum and post-quantum algorithms, like joining together quantum networks between multiple vendors in a single network, or maybe providing authentication of new devices in a quantum network which previously were not part of it. In Russia, the technology of quantum communication are now developing. We have multiple vendors, multiple companies, but in parallel, there is a roadmap to develop quantum communications, a very big strategic program from the government, which is monitored by Russian railways, and with their help, quantum networks become more and more real and more useful, obviously. We also have university quantum networks as an ability for academia to test some preliminary results, and obviously using together with post-quantum algorithms. Currently, quantum technologies now are not just in research area, and now they are used in practice. They become real tools, and this is what will happen in the future too. They will be used for different industrial problems. For example, in cybersecurity, quantum calculations can help analyze big data in order to look for anomalies in systems that would tell researchers about potential cyber attacks, or they can help with more effective response to cyber threats. So what kind of problems are solved by quantum technologies in other industries? In Russia, quantum technologies are tested in financial sector, and big banks are working with this. Let's just go through different classes. Banks are trying to solve problems connected with financial optimization, anti-fraud problems, improving the quality of credit score, many different problems. But one must say that the majority of tasks in pilot projects at the calculation level use quantum computer emulators, just before there is not enough physical quantum computers in Russia. But emulators, one must say that they just use traditional CPU and GPU backend, quite classical, but at the algorithm, they can emulate real quantum technologies. They can emulate this work. And the algorithms which were written in these emulators and this quantum, this is a very custom approach. These kind of algorithms which were created for emulators and they tested there basically with the minimum changes or maybe no changes at all can be used in physical quantum systems.
Going forward across industry,
решение сложных задач гидродинамического
the oil and gas sector is leading in Russia. They have solutions for seismics, sophisticated simulation and modeling applications. Remote access to emulators is trialed by the emulators outside the company, and it's mostly about big data. And the users gain access to emulator either a low-code interface or SDK. But in parallel, capabilities are being tested to supply emulators on premises. Because quite often, security services say that important, critical services should not be run outside the perimeter. And there are cases that one of the clear examples, VK, that is testing quantum computing internet. Gazprom Neft is one of the most active companies in Russia that's piloting quantum solutions now for seismics, hydrotectonic modeling, simulating the drilling infrastructure. A lot of other banks, Gazprom banks, Sberbank, they're piloting quantum computing. Talking about quantum communications, the financial services sector is leading as well. Banks are trying to establish communications between bank branches, for instance, using quantum communications, host-to-host bank connections, quantum resilient system of bank services, communication systems, video communication systems on quantum algorithms. The first assemblies of blockchain based on post-quantum algorithms are already present in Russia. Less so are quantum sensors being piloted. It's not that the technology is bad, it's just that it's at the early stage of development. For instance, the first cases of piloting quantum sensors to deliver medication, medicines are being tested because the sensors based on quantum effects are potentially much more sensitive. So almost all quantum technologies are being piloted, but to wrap up, it's mostly happening in the financial services sector in Russia, oil and gas, petrochemistry, but also healthcare, computing, geology, biology, and genetics are coming as well. Talk about standards. One needs to note that on an international level, quantum technologies are now in the focus of attention from governments and large business. The large vendors are also stepping up their support for quantum technologies. And for some quantum technologies, the standards database needs to be upgraded. And this is happening. Talk about the quantum threat. The growth in relevance of the quantum threat has caused changes in the approaches to national security in some companies. And we can see that in some of the countries. These documents are publicly available. So quantum technologies have now been set as separate sections in those documents. And there are countries where sets of vendors and systems integrators next to them have been assigned accountability in using quantum technology. In Russia, it's only starting to happen, but it's not yet as developed as anywhere else. And there are still a number of initiatives in Russia, and one of the most important ones is the story that's already happened. Quantum technologies has become part of the new project, data economics, and you can read the document and you'll see quantum technologies managed in many sections. There are local projects, for instance, the government of Moscow has two public reports. You can find them by QR codes, by the way. And I think it's very exciting. If the first report is mostly about a number of areas where quantum technologies can be trialed, the second report is a deep dive into healthcare, specifying how quantum approach can be used in healthcare and medicine, not only to protect data, but also to speed up computation, including genome sequencing. And these are the cases that Russia was the first in the world to implement. Talk about standards. In quantum communications, protocol standards are being developed for quantum communication in post-quantum computation as part of a profile groups DK26. New standards are being drafted for symmetric encryption. And what's important, the first implementation of post-quantum algorithms are already in existence. You can all join this work. Two algorithms now will with a high level of probability get into the standards. And they're now being developed and supported by a whole community rather than separate vendors. Actually, a lot of other things are also happening, but not everything can now be announced publicly, but we'll try to keep you informed. Yeah, so as of today, the world is actively implementing the concept of smart city. As Anton has already said, the capital city of Russia, Moscow is becoming the center for trialing such solutions. Moscow is already contemplating pilot projects involving quantum computing, quantum communications, and post-quantum cryptography in different areas, medical industry, IT, aviation, engineering, and electronics, I think, if I'm not mistaken. Also, cybersecurity will change. In essence, quantum technologies offer a new paradigm with the emerging qubit technologies, with its own hardware and software stack. And here, in cybersecurity, several promising lines of development can emerge. The first one is quantum system monitoring and security code analysis. When we're talking about quantum technology and quantum communication, a number of questions arise. How to run monitoring of quantum systems? How will the quantum AV look? What will it look like? Will it be based on the quantum physics, or will it be a classic solution? More than that, an important question for development will lie in the area of protecting privacy and protecting information property, intellectual property. So the result of such computations will have a great value for organizations and attract wrongdoers. Another promising area will be bug bounty programs. The bug bounty programs allow a lot of independent researchers to get in touch with technologies and poke them and test them for security. So we're also expecting for new attack methods to emerge. For instance, it is quite possible that the number of cloud attacks will grow. Wrongdoers will be downloading solutions from different vendors, and also
Помимо этого, возможно, что
break the resources of companies who provide access, remote access to quantum resources. And maybe ransomware producers will also focus on post-quantum algorithms so that companies attacking them could not decode the data that they had encoded. Quantum technologies will also help in cybersecurity. Cybersecurity will enjoy a higher level of information protection and a faster response if quantum computing tools are included in the classic security toolbox. If
Если подводить итоги,
I were to sum up, I would like to note that quantum technologies are actively entering our lives. They're still in some research and pilot projects, but in the future they'll become as day-to-day as classic
все в совокупности, всю картину, в том числе и вопросы
computers now. So looking forward, it's important to assess the entire picture holistically, including cybersecurity aspects. In our report, prepared by Positive Technology, together with QApp, QBoard, and Russian Quantum Center, show or highlight our research where we tried to find answers to the question of the current level of development in quantum computing, quantum communication.
С полным текстом
And
исследования
what lies in store for us in the future?
по ссылке.
You can get access to the full text of this report using this link.
В разделе исследования аналитические статьи.
So it's also available in our webpage. Thank you very much for your attention. It's been a great pleasure talking to such an enthusiastic audience. You've invested your time to come here to hear about quantum technology, and thank you for that. Thank you.
Далее поговорим о распространении киберугроз.
Further on, I will talk about the spread of cyber threats in systems that millions of people are using every day. It will be presented by Dmitry Chimeris, the founder of GenVen. The presentation will start in a few minutes. Stay with us.